Hello friends. So in previous video you have seen how to draw a pressure distribution diagram, how to calculate the depth of embedment in a anchored bulkhead, how to calculate the maximum bending moment when the sheet pile is embedded into granular soil bed and the backfill is also granular in nature. Now in this case, let's say you have a sheet pile which is penetrating the cohesive ground. Then how to draw the pressure distribution diagram? Let's say the sheet pile which is going to penetrate a ground. This ground is cohesive. And the backfill is going to be granular. And you have an anchor rod at a certain distance. So how to draw the pressure distribution diagram? The force in the anchor rod will be Fa, A for anchor. So this is the anchor rod. Let's say the top of the sheet pile is A, the bottom of the sheet pile is B. This dredge line here, it is D, and this is E. So the pressure distribution, if it is granular in nature, you know it is going to be hydrostatic pressure. So the active earth pressure at any depth, you can find it out at any depth. It is going to be the active earth pressure at any depth Z will be given by the coefficient of active earth pressure into gamma into Z. Say this distance is Z. Naturally, K gamma Z. When Z equal to H, the total height of the sheet pile is capital H. And the distance from the anchor rod up to the dredge line is a small h. So naturally, you can find out the pressure distribution due to granular backfill, and let's say the total force. So active thrust on the sheet pile will be given by half K gamma, where gamma is the unit weight of this granular backfill and phi is the angle of friction. So for the given value of phi, you can find out the value of K, which is going to be 1 minus sine phi upon 1 plus sine phi. Gamma is the granular backfill properties. So half K gamma, and the height is capital H. So it will be H square. Very simple. And the distance between from here up to the anchor rod, this distance is YA bar. So active thrust is acting at a distance of YA bar. Now, what is the surcharge at this location? Or the vertical pressure Q is going to be gamma multiplied by H. And therefore, what will be the pressure at D? Because at D, the soil is no longer granular in nature. It is going to be now cohesive. So it is purely cohesive. Therefore, phi u equal to 0 and Cu is not 0. So that's the properties. So here, at this point, there is the vertical pressure, and you know that sigma 1 or sigma 3 equal to sigma 1 into K minus 2C under root K. Now K for cohesive bed. Kc, because the phi u is 0, will be 1. And also the coefficient of passive earth pressure for the cohesive bed will be unity. Therefore, the lateral pressure at D, PA at D, will be given by the vertical pressure, that is gamma H minus 2C. Now, because this is going to rotate, as I have already shown to you that how it is going to deflect, because it is an anchored sheet pi. In my previous video, I have shown you that how it is going to deflect. So deflection pattern is known to you. Deflection pattern is known to you for a anchored bulkhead. Naturally, you feel that there is going to be active pressure acting towards the left hand side, and passive pressure will act on the right hand side. So at the dredge line, PP, the passive pressure at D can be computed very easily. So let's compute PP, the passive pressure at D, which will be given by, you know, that the passive pressure, in passive pressure, the this particular value will be given by, because here the lateral pressure sigma 1, what is the relationship? Sigma 1 equal to sigma 3 tan square alpha plus 2c tan. In passive condition, the lateral pressure PP is going to be, sigma 3 is going to be PP. So you can find out that the magnitude for passive earth pressure is, in passive earth pressure, the you know that the vertical pressure is going to be equal to, at any point Z, the vertical pressure is and the lateral pressure, you can find it out. The vertical pressure, lateral pressure is the major pressure, and therefore sigma 1 equal to PP, and this is going to be sigma 3. So this is going to be equal to PP equal to, I have already explained previously also, will be equal to gamma Z into Kp plus 2C under root. Therefore, at D, on this side, from this side to this side, what is the passive pressure? Because the vertical pressure is going to be 0, so this component becomes 0 because there is no surcharge here, and therefore it becomes 2C, and Kp is also, for the cohesive soil it is already 1, so Pp at D becomes 2C. Therefore, we can calculate PPD, the net pressure at D at this point will be PPD minus PA at D will be equal to 2C minus gamma H plus 2C. So it becomes 4C minus gamma H. So the pressure here at this location is going to be 4C. So I can draw the pressure distribution here. At this point, the pressure is going to be 4C minus gamma H, or 4C minus Q, whatever you call it. So this becomes 4C minus Q. At any depth below the dredge line, here, if the unit weight of the cohesive soil, you know it, then the pressure is going to increase on the active side in the equal magnitude as the pressure on the passive side. And therefore, when you take the difference, it nullifies each other. So finally, you will be finding that the pressure is going to be 4C minus gamma H. So at dredge line, and it remains constant up to the bottom point. So the pressure distribution finally is known to you. So from this granular due to granular backfill, you know the active pressure distribution, which is given by the magnitude here, and the magnitude of the passive force can be also calculated. This resistance offered due to the soil below the dredge line, RP, which is passive in nature, is going to be 4C minus gamma H into D. What is this D? D is the depth of embedment below the dredge line. So RP will be the magnitude of the RP is known to you, The magnitude of PA is known to you. Its location with respect to the anchor rod is known to you. And therefore, if you take moment about the anchor rod, that is about the point E, you can easily find out the depth of embedment. So, if I take sigma m about the anchor rod must be equal to 0. So, anchor rod is provided at E. Therefore, I can say that PA multiplied by this distance YA bar minus this force, that is RP, multiplied by H plus D by 2 must be equal to 0. So, from this equation 1, you already know the value of PA, you already know the value of gamma A prime, and therefore this will be how much? From here to here, this will be acting at capital H by 3. So you can easily find out this YA bar. So this is also known to you, this is known to you, this is known to you, you have already calculated. H is known to us. Only unknown is going to be D. So substituting the value of RP in terms of D and multiplying by this, substituting the value of PA in terms of H, and for a given height H of the anchored bulkhead, therefore D can be obtained. Now, if you say the algebraic sum of all the horizontal forces must be equal to 0. So, for calculating this algebraic sum, you know that Fa is acting plus Rp minus Pa must be equal to 0. These are the forces. Now Rp is already known because D is known. Pa is already known. Therefore, from this you can find out the force in the anchor rod. So Fa can be obtained. So Fa is also known. Now, if this force, this resistance force, because it is going to deflect like this. So if this force becomes 0, this force Rp is going to be 0, then your ground becomes unstable. So let's say this 4C minus gamma H, this pressure is 0. What will happen? Then your sheet pile will be unstable. So sheet pile or the anchored sheet pile will be unstable if this Kc minus gamma h equal to 0. So simple. Or the C divided by gamma h equal to 1 by 4. This C divided by gamma h is called stability number. So it is going to be unstable if the value of stability number Sn equal to 0.25. Therefore, for Sn equal to 0.25, where Sn equal to C divided by gamma h. If it is going to be this, then your wall becomes unstable. This is called a stability number. Now, if there is adhesion between the sheet pile and the adjoining cohesive soil, this is the cohesive. So if there is any adhesion, let's say the adhesion, let the adhesion due to this cohesive ground and the sheet pile, between the sheet pile equal to Ca, then this stability number Sn equal to C divided by gamma h into 1 plus Ca divided by C. So this will come into picture. Now, this already, if it is going to be 0.25, it is going to be unstable, it is a critical condition. So therefore, you can see here that if Ca divided by C becomes 0.25, then this value becomes 1.25. So this can be written as C divided by gamma h into 1.25. So you friends, you already know that what is the minimum value of C divided by gamma h? That is 0.25, and it's unstable. So, if you take it 0.25 multiplied by 1.25, it becomes 0.3. So, when you can say that when C upon gamma h equal to 0.25, or the stability number is going to be 0.25, then the this value Sn equal to 0.3, it is unstable. So you will have to multiply by the factor of safety. So for Sn equal to 0.3 into Fs, and therefore for different factor of safety you can find out the value of for a particular height h, because you know that Sn is going to be C divided by gamma h. C is the ground properties, which is going to be constant for the given ground. Gamma is going to be constant, and h, this h value is the height of the sheet pile, and therefore depending upon this so when see this Fs is going to be critical, it's unstable, so you must multiply it by the factor of safety. So when this is 0.25 and Fs equal to 1, Sn equal to 0.3 multiplied by this one. So if this is going to be, this should not be 0. This 4c, this particular value, you can see here that this 4c minus gamma h must be greater than 0. Should not be less equal to 0. Otherwise it is, or 4c must be greater than gamma h, or c divided by gamma h must be greater than 1 by 4, 0.25. So therefore, if there is an elevation, this expression holds good. So for a factor of safety, usually 1.5, you can minimum 1.5, you can find out the stability number, and you can predict what should be the maximum height of an anchored sheet pile. So friends, I have not taken the effect of the water table. Let's take the effect of the water table also and see how the pressure distribution diagram is going to change. So in the anchored bulkhead, let's say the anchored bulkhead with the grounder backfill, and anchor rod has been provided. This is the anchor rod, and this is the dredge line, and this is the ground. Anchored sheet pile, penetrating, cohesive ground. So this is cohesive ground. And this grounder backfill. Right? And this is the anchor rod. Now let's say there is a water table. Now how the pressure distribution will change? Now the pressure here above the water table, take gamma T, the total unit weight, into picture. And let's say the value is 5. Below the water table, it is going to be the submerged unit weight, and the value is 5 or 5 prime, which is equal to 5. So then, from here to here, you have to take here the active earth pressure. Let's say this height is H1. The water table will be given as K times, now above the water table it is gamma total into H1. That's the pressure. So this one pressure here is going to be K gamma T into H1. And K gamma T H1. And the total height is H of the sheet bar up to the dredge line. Now this one will be K into gamma prime into capital H minus H1. So the total pressure becomes K gamma T H1 plus K gamma prime H1, and the surcharge here Q equal to gamma T into H1, right, plus it will be the another pressure is going to be here gamma prime into H minus H1. That is the surcharge. And this side, the passive pressure is going to be constant right from dredge line up to here. And this you have seen is given by 4 times cohesion. Let's say the cohesive ground is C and phi equal to 0. C is greater than 0. So 4C minus Q, it is here also 4C minus. What is the value of Q? It is already given here. So the value of Q is known to you, right? So you can calculate it. So now the pressure distribution diagram has changed, and then you can find out the thrust and its distance from the anchor rod, and the rest is going to be same. Take the moment about this anchor rod and find out the value of D, the depth of embedment. And also you can find out the stability number. So the wall is stable. Wall will be stable up to certain height H only, because Sn equal to C divided by gamma H. As you increase H, the stability number is going to decrease. And the moment it achieves a value of 0.3, it becomes unstable. So the stability number concept is also very important. Now friends, let's say it is purely cohesive. Even the backfill is cohesive in nature. Then how the pressure distribution diagram will change? Now it's no longer granular. You see, in the anchored bulkhead, You have the anchor rod here. But now it's no longer granular. What it is? This is also cohesive. And this is also cohesive. So both are cohesive. Then in that case, you know how the pressure distribution is going to change. There will be a negative pressure, and then it becomes positive. So up to certain height, which is called the critical height, ZC. At ZC, the pressure will become 0. And this is going to be negative pressure. So minus 2C under root K. K, if you take it unity. And so this is the positive pressure, this is the negative pressure. So you can always find out the pressure distribution depending upon whether it is going to be granular or it is going to be cohesive. When we solve the example, the things we will discuss in detail. So in the next video, we are going to solve few problems to drive the point home and make the concept crystal clear. Thank you very much.